In this video, we'll do yet another example of some equilibrium calculations. I said before in this series there were 7 example problems. I was mistaken. There's actually 7 pages, but there's only 6 problems. So this one is the long one. So let's give you a second to pause the video, try to work the problem on your own, and then come back, unpause the video, and we'll go through the solution. So let's get started. A 5-liter vessel initially contains 0.0015 moles of each reactant. Find the equilibrium concentrations of iodine monobromide at equilibrium at 150 degrees C. That should say concentration. So we are given 0.015 moles of reactants. And the way they've specified that, that means 0.015 moles of this iodine, 0.015 moles of this bromine. The iodine monobromide is on our product side, so we're going to basically consider there's going to be none of that in there. Now, we're going to solve an equilibrium problem. To do that, at this point, this should be pretty routine to you. You're going to have to actually write out that Kc expression. So we're going to have iodine monobromide squared. That's our products. Notice we have 2 of them there. Concentration of iodine, concentration of bromine. Everything's a gas here, so everything shows up in the expression. That's going to equal 120. And what we're going to have to do here, of course, is we have way too many variables. We have 3 variables in one equation. So we're going to set up an equilibrium chart. Reduce the number of variables. So if you have initial conditions and you need to find equilibrium conditions, these equilibrium charts are going to help you get through these problems. So we're going to have species. There'll be 3 of them here. We will have initial concentrations. We will have change. And we will have equilibrium concentrations. So we will need 3 rows. So I've got my charts started. I'm going to have iodine in here. Going to have bromine, and I'm going to have iodine monobromide. Whoops, should be a 2 there. So, initial concentrations. We know there's some iodine and some bromine in there. Now, the iodine, 0.0015 moles, but remember initial concentration, these square brackets here, and these square brackets in the equilibrium expression mean something. They mean molarity. So if we're not given molarity, big M, then we'll have to find it ourselves, and that's what we're going to have to do here. It's 0.0015 moles in a 5-liter reaction vessel. So 0.0015 over 5. That gives me 3 times 10 to the minus 4, or 0.0003 molar. The second one is exactly the same. We have the same number of moles, the same volume, so the same concentration. So we'll just copy and paste that. The iodine monobromide, we don't have any of that, so that's a very easy calculation. 0 over 5 is 0. Now, we are going to lose some iodine, so we're going to start on this change column. It's a reactant. So we're going to lose that, so I'll give it a minus sign. How much are we going to lose? I don't know, so I will call that X. So over here to the right, I'm just going to note what I defined X as. So I assigned X to be the change in iodine concentration. So at equilibrium, our concentration of iodine is going to be 0.0003 minus X. Now for bromine, we're going to lose some of that as well. And if you look in the equation, every time we lose an iodine, we lose a bromine. So if we're going to lose X iodines, we are also going to lose X bromines. And no great surprise here, at equilibrium the concentration is going to be 0.0003 minus X. So now we're to the iodine monobromide, which is our product. We're going to make some of that. How much are we going to make? We don't know, but we do know every time we lose an iodine, we actually gain 2 of the iodine monobromides. So if we lose X iodines, we gain 2X iodine monobromide. So at equilibrium, it's going to be 0 plus 2X, or just 2X. So now we're going to plug our equilibrium expressions we have here back into the main equilibrium expression. So Kc is equal to iodine monobromide squared, that's 2X squared, divided by iodine 0.0003 minus X times bromine 0.0003 minus X. And that's going to equal 120. So one thing you might notice here, might make our lives a little easier, is that this expression actually is completely squared on the left-hand side. The top and the bottom are actually both squared terms. And we're out of room on this particular slide, so we'll move on to the next one. We're going to need to solve this equation right here. So let's copy and paste it to where we have a little room. We'll put it up here. Now, this equation is a second order equation. We can solve this with the quadratic equation, or this may be a little simpler because we don't have to do as much rearranging. We can take the square root of both sides and maybe save ourselves a little work. So what we're going to do here is going to take this equation, we're going to take the square root of over here, and we're also going to take the square root of this. So what we end up with is 2x over 0.0003 minus x is equal to whatever the square root of 120 is. Square root of 120, 10.95445,115. So we have to get x to be basically by itself. I guess the first thing we can do, and you don't have to solve it exactly the same way I do, but I think I want to get this out of the bottom. So I'm going to multiply both sides by 0.0003 minus x. So I'll get 2x is equal to 10.95445,115 times 0.0003 minus x. Now, the interesting thing here is I can go ahead and, instead of distributing this all right now, what I might want to do is just go ahead and divide both sides by this 10 term. So that will give me 2, oops, and looks like the calculator's malfunctioning, so just give me a second here to fix it. So I've got the calculator sorted out, I think. So 2 divided by 10.95445,115 gives me this 0.182,574,1858x is equal to 0.0003 minus x. So let me add x to both sides, which will give me 1.182,574,1858x is equal to 0.0003. Finally, x go ahead and get that number in there. X is 0.0003 divided by that 1.1825. So x is equal to 0.002353683873. And after all this calculating, I might have kind of forgotten what it was I was calculating. This is what x is equal to. So let's go back a page and see if we can remember what x actually is. Let me do a little copy and paste here. Get our equilibrium chart, or at least part of it. So we can remember what the heck it was we were actually going to calculate here. Sometimes you get caught up in doing the algebra and you forget what you're calculating the algebra for. So we were trying to find the iodine monobromide concentration. And according to our equilibrium chart that we made on the last slide, that's 2x is equal to the iodine monobromide concentration. So what we're going to do here, we're going to plug the value of x we calculated back into the expression for iodine monobromide concentration. And then we'll have our answer. So x isn't the actual answer, but it's easy enough to get the answer from x. So concentration of iodine monobromide is equal to 2x. So that equals to 2 times so 2 times 0.00253 683.873. So basically 0.00051, based on what I've got here, 2 significant figures is probably all I'm going to get, molar iodine monobromide. Which kind of makes sense here because we expect the equilibrium to lay far to the right. We have a good bit more iodine monobromide than those other two are going to be. Those other two concentrations are going to be really low. So, the answer looks pretty good. And with that, that's the end of this particular problem solution. Thanks for watching.